Hello everyone, myself Dr. Dhruv Kumar, Assistant Professor Department of Chemistry, Guru Nanak College, Bullada. My today's topic is supercritical fluid SFCs, their introduction and their wide applications. First, states of matter. As we know, mainly there are three states of matter: solid, liquid is gas, and another one is the plasma state of matter. Supercritical fluid exists between gas and plasma state of matter. These states are here represented according to their increasing energy. So first introduction, what is supercritical fluid? Supercritical fluid is substance that does not condense or evaporate to form a liquid or gas at temperature and pressure above its critical value. It is discovered by 1822 by Baron Charles. He discovered that critical point of a substance, the temperature above which it was neither liquid nor gas but a single phase. That phase is supercritical fluid, solid, liquid, gas, and then supercritical fluid. It is better understand with the help of phase diagram. This is the pressure, increasing pressure, this is the temperature, this is the critical point. And the highest temperature and pressure at which liquid gas equilibrium take place known as the critical point. This point is known as the critical point, and this place above this point, this place is the supercritical fluid. Such line vanish beyond the critical point at which the substance becomes supercritical and liquid and gas phase coexist. Phase is to exist. Properties of supercritical fluid: gas, supercritical fluid, liquid, solid. Supercritical fluid lie in between those of a gas and a liquid. Gas or liquid. Supercritical fluids have high density as a liquid and low viscosity as a gas. It cannot liquefy. There is no surface tension because they are unaffected by vapor-liquid boundary. Super solubility of supercritical fluids increase with the density of fluid at a constant temperature. Supercritical fluids are non-toxic, non-flammable, and environmentally safe. It is easy to produce and can be recovered by simple depressurization. Some example of supercritical fluids are carbon dioxide, water, methane, ethane, methanol, ethanol, acetone, etc. The two most common used supercritical fluids are carbon dioxide and water. These two are most common and widely used. Supercritical fluids are proving to be useful because they have properties to similar both liquid and gas. They have both types of properties. They have ability to dissolve substance like a liquid and permit through solid like a gas. These properties are used in their applications. Now, applications of supercritical fluids. Supercritical fluids have various industrial process and technology in their application, like drying, synthesizing, crystallizing, mixing and dispersing, addition, extraction, cleaning, foaming, immersion dyeing, forming film, etc. We will discuss detail. First, application of supercritical fluids in food and drinks. Organic food products can be extracted using supercritical fluid. Decaffeinating coffee, creating natural coloring, sterilizing milk, and deodorizing fish oil are some of the use of in supercritical fluids in food and beverage, etc. Cosmetic. Natural antioxidants are a common ingredient in cosmetics. These antioxidants can be extracted from a wide range of fruits and vegetables by using supercritical carbon dioxide. Tocopherol, vitamin E, polyphenol, and carotenoids are some of the antioxidants. The fragrances of flowers are also extracted by supercritical fluids. Now, pharmaceutical industry. Supercritical fluids help in the processing of plant extract used in the pharmaceutical industry. In order to increase medication solubility through particle size control, they are also used in the micronization of active pharmaceutical ingredients. Supercritical fluids used in pharma industry mainly bioimaging, tissue engineering, particle engineering, and delivery systems. Application of supercritical fluids in plastics and polymers. Supercritical CO2 diffusion modifies the physiochemical properties of polymer by altering their structure. This is the very important property. Glass transition temperature can be lowered with the help of supercritical fluids, carbon dioxides. Supercritical carbon dioxide is also used to purify polymer from residual solvent and to synthesize them with composites. Drying industry. The lack of surface tension in supercritical fluids, they can dissolve solvents from extremely porous structure without altering the internal three-dimension structures. This results in the material that is dried without containing solvent and which remain intact inside. This technique is used in dry cleaning service to replace undesirable chlorinated solvents. In textile industry, supercritical carbon dioxide is an alternative solvent that can be used to dye textiles, tanning leather, etc. Supercritical fluids offer cost-effective and environmentally safe solution in both cases. Supercritical carbon dioxide is an environment-friendly substance for chlorinated solvents in dry cleaning. Now, supercritical fluids in chromatography. Supercritical fluid chromatography is a normal phase chromatography, and supercritical fluids are used as a mobile phase. The HPLC method and this principle are similar. It analyzes the separates lightweight thermally liable molecule and chiral compound. It has advantages over HPLC and gas chromatography because it can be used with the universal flame ionization. It is mainly used in the pharmaceutical industry. Fish oil, polymer, plant extracts, and vegetable oil are also purified with the help of supercritical fluid chromatography. Sterilization. Supercritical fluids are used to sterilize medical equipment because they can break down the cell wall of certain bacteria, virus, fungi, and yeast. Since this mechanism is still not clear, this property is not used frequently. Impergination. Supercritical fluid can be used for impergination procedure. When mixture is passed over supercritical fluids such as CO2 dissolve in active ingredient and deposit it onto the solid surface. Further, dyeing polyester and other polymer fiber is significant application of supercritical fluids. Chemical transformation using supercritical fluids. Many reactant and products are highly soluble in supercritical fluid. As we know, supercritical fluids can dissolve a wide range of substances. Applications include biomass conservation, fuel processing, various forms of catalysis and polymerization. Supercritical fluids used in place of organic solvent in industrial and laboratory procedure. The two most often used supercritical fluids, as we discussed earlier, carbon dioxide and water, which are regarded as green solvent because these are cheap, non-flammable, non-toxic, and provide large yield in the variety of chemical transformation reactions. These are some common chemical transformation reactions like ammonolysis, polymerization, oxidation, metathesis, hydrogenation, hydroformylation, Fidelcraft reaction, alkylation. These are very few of chemical reactions that used with the help of supercritical fuel. There are many more reactions. Now, Supercritical fluids in green chemistry. Supercritical fluids are frequently cited as the key tactic in green chemistry to enable new clean technology and replace volatile organic solvents. Many chemical transformation, as we discussed earlier, supercritical carbon dioxide is used as a solvent as well as catalyzed to facilitate their intimate contact of reactant. The different application of supercritical carbon dioxide depend upon its solvent power, which allow them to take full advantage of its liquid-like characteristics. This process have a greener chemistry component that goes beyond simply substituting supercritical carbon dioxide for unwanted volatile organic solvents. Conclusions. Supercritical fluids have greater potential as media for chemical and biochemical reaction because of their unique properties. Supercritical reactions provide opportunity to adjust temperature or pressure to modify solvents properties, improve the solubility of reactants and product to reduce interface transport limitation in order to enhance reaction rate and also improve selectivity of the reaction. It is an alternative organic solvent. Further, supercritical fluids can help environment friendly industrial process and promote greener chemical industry. They offer the tool essential to develop chemical engineering processes that are sustainable. Supercritical fluids offer financial advantages as well as, for example, the use of organic solvent for extraction and downstream processing rise the cost of production. Pesticides from soil and other environment pollutants can be eliminated with supercritical fluids. Unwanted imprecise steps are added by solvent evaporation and solute recovery, which may need to replace. Highly compressed gas like CO2 are used in supercritical fluid extraction process. Recovery is considerably simpler, safer and more effective. Additionally, they are non-toxic, non-flammable and friendly and safe. They are also simple to produce and can be retrieved by simple depressurization. These are the references that shows the advantages and uses of supercritical fluids. Thank you very much.